Welcome to the Deep Dive. We're here to take that dense research you sent over and really unpack it, find the genuine insight. Today, we're diving into something pretty universal if you think about it. Plastic getting wrecked by the sun. You know, polymer degradation.
It's a huge issue. Polymers are literally everywhere.
Absolutely. Advanced components, simple packaging, you name it. But stick them outside, and UV radiation just acts like a chemical wrecking ball.
Yeah. It speeds up failure, fades the color.
And adds tons to that ever-growing pile of plastic waste. It's a big problem.
Definitely.
So today we're focusing on one material in particular, polylactic acid, PLA. Anyone into 3D printing knows this one.
Oh yeah, very popular. Cheap, easy to print with.
But, and this is the key thing, it's really sensitive to UV. Put a standard PLA print outside. It gets brittle, cracks, doesn't last long at all.
Not ideal for anything meant to be durable outdoors.
Exactly. So our mission today, the sources you sent, outline this really novel approach, almost like a nanoscale double punch, using two advanced coating techniques together.
Right. It's about finding that sweet spot where two methods that kind of fail on their own suddenly work brilliantly together. That synergy.
They're looking for that breakthrough.
Yeah, we're moving past just mixing stuff into the plastic bulk.
Good.
This is about building, like, atomic-level armor.
Atomic armor, I like that.
The core idea uses zinc oxide, ZNO, coatings, but the how is crucial. It's a combo of vapor phase infiltration, VPI, and atomic layer deposition, or ALD.
Okay.
And the big hurdles. Doing this effectively without damaging the heat-sensitive PLA and making sure it stays transparent, we need serious durability, engineered super precisely.
Okay, so before we get to the new stuff, let's quickly touch on why the old ways don't quite cut it. It sets the scene, right?
Good idea.
Traditionally, you'd add chemicals like HALS, hindered amine light stabilizers, or maybe fillers like titanium dioxide.
Right, those are common, but they have drawbacks. There are regulatory concerns cropping up for some. And maybe more fundamentally, just mixing them in doesn't guarantee even protection. You get clumps or areas with less protection. It's hard to disperse them perfectly uniformly, especially at the surface where the UV hits first.
Right, so bulk additives aren't a perfect shield. What about coating the outside? Like painting it with something protective?
People try that too. Liquid-based methods like Sol Gel, they can work, but you often end up with liquid waste to deal with.
Okay.
And getting a perfectly uniform coat, especially on complex 3D shapes, that's tricky.
And other vapor methods, like standard CVD, chemical vapor deposition?
Generally too hot, CVD often needs high temperatures, which would just melt or warp PLA. You need something gentle, low temperature, but also super precise.
Which brings us to one of your key players, ALD, atomic layer deposition.
Exactly. ALD is really the gold standard for precision coating. It's solvent-free, which is great.
How does it work, basically?
Think of it like atomic scale spray painting, but incredibly controlled. You expose the surface to one chemical precursor, it reacts, you flush it out. Then expose it to a second precursor, it reacts with the first layer, flush it out. Layer by atomic layer.
Wow, so you build the film up atom by atom?
Pretty much. It gives you amazing control over thickness and ensures the coating follows the surface contours perfectly. It's conformal, like building with atomic Legos one layer at a time.
Sounds perfect. So why doesn't everyone just use ALD on plastics like PLA?
Well, here's the catch. The fundamental problem with ALD on many polymers, PLA included.
Okay.
Polymers like PLA often have, well, chemically inert surfaces. They lack the necessary sticky spots, chemists call them nucleation sites, for the ALD precursor molecules to effectively grab onto and start the growth process.
So it's like trying to paint something super slippery, like Teflon.
That's a great analogy.
Yeah.
The precursors just don't stick well, so the growth is incredibly slow, patchy, non-uniform. Sometimes it barely grows at all. You waste a lot of expensive precursor chemicals, too.
Okay, so ALD has the precision, but it can't get started properly on the PLA surface.
Right, and that leads us to the other technique, VPI, vapor phase infiltration.
VPI, okay. How is that different?
It uses similar chemistry like the precursor gases, but the goal isn't just surface growth. VPI is designed so the precursors actually diffuse into the polymer.
Into the plastic itself?
Yeah, into the tiny free spaces between the polymer chains, the free volume. It sort of infiltrates the material near the surface.
What does that do?
It creates this hybrid material, part organic polymer, part inorganic stuff like ZNO, mixed together within the plastic matrix. It can be good for, say, making the bulk material stronger or maybe blocking gases better.
But for UV protection, UV attacks the surface.
Exactly. And that's the limitation of VPI alone for UV blocking. Because the protective inorganic material is dispersed inside, not concentrated as a solid layer on top, it doesn't form an effective continuous shield against incoming UV light.
So let me get this straight. We have ALD, super precise surface coating, but it won't stick well to PLA. And we have VPI. It sticks great and goes inside the PLA, but doesn't form that crucial protective surface layer.
You got it. Individually, neither is the perfect solution for creating a robust UV shield on PLA. That's the puzzle they needed to solve.
Okay, so the puzzle is set. Neither ALD nor VPI alone is the answer.
Right. Conventional thinking might stop there. But the researchers had this really elegant hypothesis.
Which was?
What if you use VPI first, not primarily for its own protective effect, but to deliberately change the surface and just below the surface chemistry of the PLA, use it to seed the material?
Seed it. You mean create those sticky spots that ALD needs?
Precisely. The idea was use VPI to put down the nucleation sites, effectively preparing the surface, then follow up with ALD to build the actual high-quality protective layer on top of that prepared surface.
Okay, a seed and shield strategy. Clever. Did it work? What did the results show?
Did it work? It worked spectacularly. Let's look at the hardcore data on physical degradation. They blasted samples with intense UVC light for 30 minutes, really harsh conditions.
Wow.
And the results for the controls were, well, brutal. Untreated PLA, gone. PLA treated with only ALD, gone. PLA treated with only VPI, also gone.
Gone how?
They measured the thickness remaining. For all those samples pristine, ALD only VPI, only less than 10% of the original thickness was left. The UV just obliterated them, turned them almost to dust in that short time.
Wow. Less than 10%. That's basically complete destruction.
Total failure. Now compare that to the samples treated with the combined VPI plus ALD process.
The seed and shield approach.
Exactly. They needed a certain amount, mind you, at least 3 VPI cycles to seed, followed by at least 250 ALD cycles to build the shield. Those samples, after the exact same 30 minutes of intense UV,
What happened?
they retained over 96% of their original thickness.
Wait, 96% compared to less than 10?
Yep. From disintegrating in minutes to being almost completely untouched. It's a night and day difference.
That's incredible. So they quantified this somehow. You mentioned a protection factor.
Right, the PF, protection factor. It basically compares the degradation rate. The VPI plus ALD treated films showed a PFF, meaning they had over a 100-fold reduction in their degradation rate compared to the untreated PLA.
100 times more durable. That's not just an improvement, that's transforming the material.
Fundamentally, it redefines what that PLA can withstand.
Okay, so the physical structure holds up. But what about the chemistry underneath that coating? Was the plastic itself still breaking down chemically, even if it wasn't eroding away physically?
Yeah.
How did they check that?
Good question. They used a technique called FTIR Fourier transform infrared spectroscopy. It looks at the chemical bonds in the material.
Yeah.
They tracked a specific chemical signature of PLA, a peak related to its carbonyl groups, around 1750 on their charts. In the samples that fell apart, the pristine ALD only, VPI only, that peak completely vanished.
Meaning
Massive breakdown of the polymer chains themselves. Photochemical bond scission, chemists call it.
Yeah.
The UV was just chopping the molecules apart.
And in the VPI plus ALD samples, the ones that survived physically.
Yeah. In those films, the PLA peaks remained strong and consistent, almost unchanged. It showed the coating wasn't just physically blocking erosion, it was successfully stopping the underlying chemical reactions, the bond breaking, caused by the UV light.
Wow.
They calculated a chemical protection factor, too, based on those peaks, and it was over 320. So the barrier cuts down the fundamental photochemistry by more than 2 orders of magnitude. It's real protection.
Okay, so the results are dramatic. VPI plus ALD works incredibly well. Now, the big question, why?
Right.
What exactly did that VPI pretreatment do to make the ALD suddenly work so effectively?
Right, that's the mechanistic insight. How did VPI change that surface?
You said earlier it was like turning Teflon into sandpaper for the ALD. How did they actually measure that change in stickiness?
They used a very sensitive technique during the deposition process itself. It's called a quartz crystal microbalance, or QCM. It's like an incredibly precise scale that weighs the film as it grows, cycle by cycle. This lets you calculate the growth per cycle, the GPC. How much material, in this case ZNO, is actually depositing in each ALD cycle. It's a direct measure of how efficiently the process is working.
And what did they find? What was the GPC for just ALD on plain PLA?
Remember, we said ALD alone was really inefficient. The QCM confirmed that. The GPC was tiny, only about 5 nanograms per square centimeter per cycle. very poor growth, confirming that lack of nucleation.
Okay, 5 nanograms. And when they did the VPI seeding first.
When they ran those VPI cycles before starting the ALD, the GPC measured during the subsequent ALD stage shot up dramatically,
How much?
up to almost 80 nanograms per square centimeter per cycle, so
my-
79.7 NGC meter to be precise.
Whoa, from 5 to nearly 80.
Exactly. That's more than a tenfold increase in the amount of ZNO deposited per ALD cycle. It's massive.
So the VPI absolutely did create those sticky spots.
Unquestionably. It effectively activated the polymer surface, making it receptive to ALD. The growth rate became similar to what you'd see doing ALD on a standard, easy-to-coat material like silicon or quartz. They actually compared it. ALD on quartz had a GPC around 74 NEC meter RTC says. So VPI made the PLA surface behave almost like quartz for ALD growth.
That's compelling physical evidence. But how did they confirm chemically that the VPI put zinc into the surface and subsurface to act as those seeds?
For that, they turned to another technique. XPS, X-ray photoelectron spectroscopy. XPS analyzes the elemental composition and chemical states right at the surface.
And it found zinc.
It found zinc, yes. But the really clever part was they used a gentle etching process to remove the topmost ALD layer and then did the XPS analysis.
To see what was underneath.
Precisely. And even after etching off the main ALD coating, they still detected zinc features. That confirmed that zinc species from the initial VPI step were present at the original polymer surface and even slightly beneath it within the polymer matrix near the surface.
So the VPI infiltration was key. Did they know what form the zinc was in, what made it a good seed?
Yes, XPS can give information about the chemical state too. They identified the zinc species introduced by VPI as being hydroxylated zinc, basically. Zinc atoms bonded to OH groups, forming something like ZnOH2.
And those OH groups are important.
Very important. Those hydroxyl groups are known to be excellent nucleation sites for ALD growth of oxides like ZnO. VPI essentially decorated the PLA surface and subsurface with these perfect little chemical anchors for the ALD precursors to latch onto.
So VPI provides the chemical handshake, and ALD builds the armor on top of that.
That's a perfect way to put it. And when they looked at the final structure with high-powered microscopes, SEM and TEM,
Electron microscopy.
right, they saw exactly what you'd hope for. A distinct, very uniform, dense layer of polycrystalline ZNO sitting right on the surface, about 55 nanometers thick.
Consistent thickness.
Very consistent. And critically, it was clearly integrated with the polymer beneath where the VPI had infiltrated. It wasn't just sitting loosely on top, it was anchored. An integrated, hybrid protective structure.
Okay, this coating sounds incredibly tough. 100-fold improvement, uniform 55-millimeter layer. But like you said earlier, for many applications, it has to be clear, right? Especially for packaging, maybe screens, even car parts. Did the ZNO layer block visible light?
That's a critical point. A coating's no good if you can't see through it when needed, so they tested the optical properties carefully.
And the UV blocking was good?
Excellent. The VPI plus ALD layer absorbed up to 94% of the harmful UV radiation right across that damaging spectrum from 200 to 400 nanometers, so it does its primary job really well.
Okay, great UV blocking. But the visible light, did it make the plastic hazy or dark?
That's the crucial part. They measured the transmittance in the visible spectrum, specifically around 550 nanometers, which is where our eyes are most sensitive. The transparency remained high. The transmittance only dropped modestly from about 95% for the untreated PLA down to about 83% for the coated PLA.
So still mostly transparent.
Yes, 83% transparency is still very clear for most applications. It shows the 55 nanometer layer is thin enough that it doesn't significantly scatter or absorb visible light. Minimal haze, good clarity, that's a big win.
Definitely makes it much more practical. Okay, so the science looks solid on flat films, but real-world objects are often complex shapes, maybe 3D printed parts with lots of edges and curves. Does the protection hold up on those? Did they test it on something more realistic?
They did. They used 3D printed PLA mesh structures as a kind of torture test. These meshes have a high surface area, complex geometry, lots of potential weak spots where degradation usually starts.
It makes sense. So what happened to the meshes under UV?
Well, the comparison was, again, really stark. The standard untreated PLA meshes, after just 7 days of that same intense UVC exposure,
Which simulates.
they estimated it simulates about 220 days of typical outdoor solar exposure, so quite a long time in real-world terms.
Okay, 7 days accelerated test. What happened to the untreated mesh?
It became extremely brittle. Just touching it caused it to break into small fragments. Complete mechanical failure. Useless.
Fell apart. And the mesh is treated with the VPI plus ALD process.
After the same 7 days of UV, they remained completely intact. You could handle them, bend them. They retained their original flexibility.
Wow.
It was clear proof that the protection wasn't just a lab curiosity on a flat film. It works effectively on complex macroscale 3D structures, preserving not just the material itself, but its actual mechanical function. Hashtag tag outro.
Okay, let's wrap this up. If we boil it down for everyone listening, the real story here seems to be about synergy, right?
Absolutely.
BPI isn't just another coating technique in this context. It's the critical enabler. It's doing the prep work, laying down those chemical seeds
Those nucleation sites.
that then allow the super precise ALD process to build this incredibly effective, uniform, transparent ZNO shield on a plastic that it normally wouldn't even stick to properly.
Exactly. You're using one atomic level process to fix the limitations of another.
And the result is this massive jump in durability, that 100-fold improvement that neither process could achieve on its own.
It's a perfect example of the whole being greater than the sum of its parts.
So thinking bigger picture now, if this kind of low-temperature, potentially scalable process can make a common UV-sensitive plastic like PLA last 100 times longer outdoors, what does that mean?
Well, that's a really exciting thought to leave people with, isn't it? Think about all the plastic products currently designed for outdoor use that fail prematurely simply because of UV damage.
Car bumpers, dashboards, construction materials, outdoor furniture, signage, packaging left in the sun.
All that stuff. If you could extend its functional lifespan by years, maybe even decades, using a coating like this, what impact would that have on the sheer volume of plastic waste we generate?
It could be huge. Less replacement, less manufacturing, less waste ending up in landfills or oceans.
Could technologies like this fundamentally shift how we design durable goods and combat the global plastic accumulation crisis? That's the potential transformation we're looking at, something to really think about.